So Olivia, you just jumped in. We're using the table that I posted on CM Connect on how to read the Z-score table. That's what we're going to kind of play around a little bit today.
Okay, awesome.
We'll probably talk a little bit about regression. I just realized that requires tables because everything in the book says to use technology. So we probably won't get to that as well today. I'm probably just going to talk a little about regression anyway. And then we'll move on to, like I said, finance next week. So the negative Z-scores, right? So on the negative table, just to make it easy. So the key with this is, and we'll go back to the OneNote here in a minute, is this is all based off a normal distribution, which looks like a bell curve like they have drawn on top of the sheet I've shared with you, right? And the key with using this chart is it's centered at 0, which is the mean, right? And we represent that by the symbol mu, which kind of looks like a backwards U or a tail with a U. It's a Greek letter. And it has a standard deviation of 1. And this guy is called a sigma. And we'll really get into a lot of these symbols and statistics. But to use this table, you have to have a mean of 0 and a standard deviation of 1. And you notice they have Z labeled here along the horizontal axis. And anywhere along this axis are Z-scores, right? And that is what this column is. And so when we calculate Z-scores, to go down the first column, it is numbers in the ones place and in the tenths. So basically 1 decimal point. And then to go across the top row, we are in the hundredths place. So you use these 2 rows here to create a 2 decimal number. So I'm just making up numbers right now, and then I'll go to the OneNote to show where they come from. But right now, I just want to make sure we know how to read the table. So if I tell you have a Z-score of negative, so Z-score equals negative 2.46. My first 2 numbers are the negative 2.4. So I come down the left column and I find negative 2.4. Then this number is in the second decimal place. So I come over here to find 0.06. So I break the number up. First column, first row. And then you just drag your finger across. So the other 2 line up. So I come all the way over till I'm under the 0.06, and my Z-score is 0.0069. I mean, not my Z-score, my answer. So what that is showing me, horrible distribution here. But if I'm at negative 2.4, if this is zeros in the center, so negative 2.46 is kind of over here, right? If I draw a line up and then I color this piece, then the amount of it that is colored is 0.0069. That's how much of the graph is colored. And that's why on here, they always have a normal distribution. They have it labeled 0, and they have part of it colored. So to use this table, you must be colored to the left, always and forever. That's what these values represent. Any questions where I got those values from? All right, let's try another one then. What if I tell you the Z-score equals negative, because we're on the negative side for now, negative 0.15. Center at 0. I'm at negative 0.15. line up, how much of this is colored? So I have to come down here to negative 0.1. And then one more. 5 is this column. 1, 5. So almost all the way to the very bottom, right? And I get an answer of 0.4404.
Yep. Yep.
0.4404. So the z-score is an event, right? And this is what we talked about with rules of probability, right? This is what we're looking for. The numbers inside the table are probabilities. So this really is 44.04%. So just under half of the graph is colored if I have a z-score of 0.015. So obviously mine's not drawn to scale. And if I was dead center at the mean, and I colored to the left, right, that would be a 50% of the graph is colored. Because I'm at the middle, right? And that's what the middle means. So if I scroll to the bottom again, and I go to negative 0.00, you see I get a 0.5. Well, if I turn the page over, there are my drawings just so they're not chasing us around. And I go to the positive side, you see the positive side starts at 0.00, which is 50% as well. That's where the breaking point is. The breaking point is at the mean. So if my z-score is to the left of the mean, I am less than 50%. If my z-score is to the right of the mean, I am more than 50%. So if you look at the positive side, all these numbers are greater than 50%. And if the entire thing was colored, that would equal to what?
1. All of it.
1 or 100%. So if you scroll to the very bottom of your, if you look at the very bottom of your chart, you see it ends at 0.9999, right? So they don't quite go 100% because it only goes up to 3.5, but basically it says if you go 3.5, you're pretty much covering the entire graph. And if you go to the negative side and look at where it starts at 0.0001, which is negative 3.5. So long as my z-score is between negative 3.5 and positive 3.5. That covers, according to our table, 99.99% of the table. I mean, of the graph. Right?
Yeah.
So, that's how you read the table. And there is really only one purpose for this table. It was used before technology, right? So there's really no point to it in today's world anymore because we can use technology to do all this. But a lot of times, unfortunately, we still teach it this way. I would love not to teach it this way, but I cannot get all my students to embrace technology. So we, unfortunately, are stuck here.
I don't like change.
Yeah. Yes, I've gotten a lot of that lately.
Come on.
So that's how we read the table. Now, a couple key pieces to read in this table. All the values in this table, again, are only if I color to the left. So in statistics, I make all my students color. So if you like to color, this is a great lesson. If you hate coloring, I still make you color anyway. Right? Because color want to help you know if you've finished the problem or not. Where it gets tricky, right? And I want to make sure we can read the table because this is always seems to be the tricky part once we go into actually doing calculations. is say I draw a picture. Dang, why did I get rid of that? I don't want to get rid of that. And now I do a z-score of negative 1.02, but I've colored to the right.
Would you just do the same thing and then take the opposite of?
Yes, exactly. So I'd go find negative 1.02, negative 1.000102. So there's that 1.1539. So this is 0.1539. So to do the opposite means I do what?
Check one.
Yeah, I do 1 minus 0.1539. And my answer is? Yeah, I'm with you. We're going to calculator. 8461. So this is why I like the color, right? Because it reminds me, like, the table will find my part of my answer, but I have to do one extra step because I colored the wrong way. Because the numbers in the table are only numbers to the left. But it's not bad to find the right as long as you remember our friend, the complement rule, which we learned back in probability. Which means going to the opposite. So, coloring to the left, easiest. Coloring to the right, not too bad. One little extra step. All right. Any questions on where I'm getting these figures from?
No.
Good. All right. So we'll do the hardest for last then. Now, draw my bell curve. And say I get a z-score, I'm just going to pass so we can see the numbers, of negative 1.96 and 1.37. And I've colored in between the two numbers. What should we do now?
Huh.
Let's see here. You take, all right, we're going to start with 1, and then we're going to subtract the value of negative 1.96 out of that because it's not colored in.
Okay.
And
so you're saying we're going to go find this guy first. I like that. So let's go find negative 1.96. So negative 1.96 is 0.0250.
yeah.
That means he's 0.0250. Okay.
And then if you took the value of 1.37
Okay.
and then took the complement of that, you'd know the other part.
Okay. So let's pause for a minute because you're on the right good path. So I got to scroll down because I got to go to find find a positive 1.37. So 1.37 is 0.9147. So change my color here. So for this one, that means this is I didn't click on my draw. There we go. 0.9147. Okay.
Which is everything to the left of that line.
Yep.
And so now all you gotta do is subtract the red from the blue.
There you go. 0.9147 minus 0.0250.
Wait, how did you get the blue number?
You go to your positive side and find the number 1.37.
Oh, okay, thank you.
Yeah. Yeah, so the blue number is everything that's scribbled in and then everything that's red.
Right. Yeah, I get that.
Yeah, Dylan is right on, right? So if the 0.9147 is all of the black, but it's also the rest of this blue piece, right? Well, we already know the little blue tail is 0.025. So if we cut the tail off, we are left with just what we have. So that's why we are subtracting.
Yeah, there's a couple different ways to do that. I was going to do a more convoluted way. I was going to do an extra step.
Yeah, I felt you on that path. That's why I kept pumping the brakes on your process, because I figured you'd catch it before you got there. But your way wouldn't have been wrong. I saw exactly where you were going. You were going to find the two tails. Yep. So lots of different ways to attack this. And this is why I like to draw the pictures, right? And even if I use technology, I still like to draw the pictures, because I am inputting it correctly into technology. Because Excel can do this for you. The issue with Excel, it is also programmed to go to the left. So even when you read numbers using technology, they've been programmed based on these tables. So it also reads to the left. TI 84, 83 calculators, you can put the numbers that you want in, and it'll actually do the subtraction piece for you. So it will do this piece, and the TI calculator will actually give you this answer. For Dylan, because he's in, because you're in calc, right?
Yeah.
Yeah, if I actually integrate, have you guys got the integrals yet?
Yeah.
Yeah, if I integrate from 1.96 to 1.37, I'm not going to write the formula out, but if you put in the normal formula, it will also give you that answer. This is why someone years and years, I mean, long time ago, before I even started doing statistics, the reason they came up with tables is most people can't do calculus. So the calculus came up with tables for people that don't do calculus, right? Before technology. Now there's technology and calculus, so we don't really need these tables anymore. No one uses these tables in the real world anymore. We use technology or calculus to find our answers. But that's exactly what calculus does. An integral finds the area under the curve, and that's exactly what probability is. Probability is what percentage of the curve is colored. So that's how these things are all related. This table is just an extra step for people that don't want to use technology. But coming off my soapbox of why we should use technology, any questions on how to read the table and how we use the table how we manipulate the table to answer the questions we're asking for? I think the only one we're missing is Brianna. Oh, Emma too. No, Emma's here. Go ahead. Olivia, you may have to start again. You definitely do not have a good connection. You were roboting pretty good.
I just said, I've seen this in stats once or twice. Well, like, yes. Can you hear me now?
Yep.
Maybe I'll put in the chat. Uh-oh.
So now that we've figured out how to read the table, because that's usually my biggest problem when I teach this, it's not really the procedures, it's how to read the table. So I'm going to shrink my table down for now. We'll go back to our OneNote. I'm going to shrink my boxes just so they're out of my way. And so this is what we started last class, right? So I drew two normal distributions. I did the standard normal, and we talked again about the empirical rule. And the purpose of the empirical rule is how, if we take regular size steps, I can get the answer pretty easily. What the tables do is allow me to take a different size step besides a full step. That's right, good. So you've seen this before, so that helps. The problem in the real world is very few things have a mean of 0 and a deviation of 1, right? Usually we have a mean of some other value and a deviation of some other value, right? So that's where life gets a little trickier. So here, Say we make something that holds 40 calories, right? And it deviates by 5 calories. So here is my normal distribution of that. And so what we have to do is we have to do this extra formula. Let me get into my OneNote here. Let me give me some space to work. Is called the Z formula. And the formula for a Z formula is Z equals X minus mu all over sigma. And what I always like to add is not in the formula because it doesn't technically need to be there to be written properly, but if you just blindly follow this formula and put things in your calculator, it doesn't work out nice for you because you actually have to do the subtraction before the division because we have a single denominator. So I always recommend my students add parentheses to the formula. Therefore, they can remember to do the subtraction first. So what does this mean? So the Z is what we were just using on the table. That is the value for the table. That is your Z score. Mu is the mean, right? That is the number it's centered at. Sigma is your standard deviation, which we've learned in earlier in the course, in 8.3, sorry. That's how big of a step we're taking. What X is what I like to call the event. It is what you are looking for. So if we use our calorie problem here, and I have a mean of 40, horrible bell-shaped curve here, with a deviation of 5, and I always like to write mine to the side, but for no other reason, just to remind me. And say I am looking for the probability that I am going to be at 33 or less, right? So then I color. Less means I color to the left, right? So now I just start putting numbers into the formula. Z equals, my X is where I started coloring, so that's my 33. My mean is 40, so I subtract a 40. And I divide by my deviation of 5. And I'm going to throw this horrible guy into parentheses, just so we don't mess up our calculations. And then I go to my calculator, parentheses, 33 minus 40, close parentheses, divided by 5, enter, and I get negative 1.4. So that is a Z-score. And for a Z-score, I need 2 decimal places. So since there's no number there, I will just add a 0. So now I go to my little chart. I'm not going to bring mine back up because you all can see it. We know how to read it now. And I find negative, which tells me I'm on the negative chart. And I go to negative 1.40, and I get an answer of 0.0808. Any questions where I got any of these numbers from? So really what this answer is if I make some product is 40 calories, the probability, actually I'll just type it instead of trying to write all that out. Erase. So what I basically answered here is highlighted. Fine. What is the probability of randomly selecting one item that has 33 calories or less. That's what kind of question we're answering, right? Based on a mean of 40 and a deviation of 5, right? One probability of picking one of those items would have an 8.08% chance. That's what this thing just told me. Questions?
No, that's pretty cool.
All right. So let's just change it up a little bit. I'll delete this. I'll leave it on here. That way people can come back and watch the video if they want. So my next question then be, what is the probability of randomly selecting one item that has more than 47 calories?
Oh, I thought you were going to make it easy for us.
Oh, I always like to draw because I'm a visual learner. So I draw my distribution. Shoop. I know it's centered at 40 because I haven't changed the problem. I know I have a deviation of 5 because I haven't changed the problem. 40 is there. And 47, yeah, about right there, we'll say. Draw my line up. I want more than, so I color to the right. Now I calculate my Z. Z equals, parentheses, 47 minus 40 divided by 5 equals. Oh, we just got the exact same answer? How the heck did I do that? Oh, because I went in 3 both directions. I mean 7 in both directions, that's why. Now I got a positive 1.4. This actually works out good because it gets me to prove a point here. So now I go to my table. So table, and I get a value of 0.9192. But I have to do what with that number?
The complement.
I have to do the complement because I'm colored the wrong way. So go back to my draw. So this is 0.9192. So therefore this is what?
0.0808.
0.0808. Why did we get the same answer?
They're both 7 away from the center.
They're both seven away from the center. A normal distribution is symmetric. So remember that what we're looking for is how far from the center are we, right? The first problem, we stepped 7 to the left. This problem, we stepped 7 to the right. We got the same answer because we went the same distance. This one's answer is also 8.8%.
Does stats only teach normal distribution?
Yes. We do a little bit of, I do a little bit more when we get into confidence interval and hypothesis testing, we do a little bit of the t and a little bit of a chi-squared, but that's as far as we go. How are we doing? Not too bad? Now, what I beg of all of you is don't forget this over summer break. That have to take statistics, or at least don't forget it all. So when we get to chapter 6, this hopefully will all come back to you. So if we do one more, and then we'll probably quit with normal distribution because there's not much more to it than this. What is, oh, back to my highlighter. I got too close to my other paragraph. What is the probability of randomly selecting, and I'm purposely putting, I still spell probability wrong typing, one item, because if we pick more than one item, it's a whole new thing. We'll learn that in statistics. What is the probability of randomly selecting one item that is between 35 and 45 calories?
If you do more than one item, is that the whole like square root of n?
Yep. Yeah, that's the central limit theorem.
Yeah.
Now we're doing 35 to 45.
Yep. And this one, I will slow down here for a sec and let's see if you guys work it out. I'll still draw these geometry picture because I like drawing the normal distribution. The deviation of. This is where I feel statistics starts to get a little fun. But that could be just me. I do appreciate doing this on a computer because when I'm in the classroom, I spend so much time erasing, drawing all these things all over the board with all the pretty colors. So let's see here. We have anyone have an answer yet?
Yeah.
What you got?
0.5762.
I did not get that answer.
Oh no.
I got 0.6826.
I got that answer.
What do I do? Hold on. Recalculating. 5 divided by 6.
Oh, you get the wrong deviation.
Oh, 5
Deviation's
divided by
5.
Oh. Oh. Whoops. How'd I get? I don't know where I got the 6 from. All right. So it's a deviate. Okay, so then we just get 1.
Yep. We basically made one step to the left and right.
Oh.
And I purposely did that because if we scroll all the way to the top here, our empirical rule says if you are one step to the left and right, that's about 68%, right?
Yeah.
Now, you actually can find the exact value, which is 68.26%. So this is what the empirical rule is kind of based off. And that is kind of the big difference. Until this point in statistics, we use the empirical rule for everything. After we get to chapter 6, I say you cannot use the empirical rule anymore because now you can calculate the exact value you want. Pretty good?
Oh yeah.
Yeah, not a lot to this one. This one's a little, like I said, this one kind of gets a little fun. Using statistics, when I have students that are really struggling with this, it's the table's confusing to them, which takes a little bit, or they don't know what their symbols are by this point. And then statistics is extremely hard if you don't know what the mean is and the standard deviation. You all only learned it this week, so it's good that we're going to already get this. By the time we get to this, we've been talking mean and standard deviation for about 10 weeks. So there's a little of this thing. So a lot of times you see -2 to 2, right? So how would you interpret it when you have a z-score less than -2 or greater than -2? What that's saying is, if I go back up here to the empirical rule, what is it when I am out into these tails? So when I'm 2 away, like when I'm out here and out here, right? Well, if this is 95% in the middle, then there's 5% in the 2 tails, right? So this is where we get this thing about being significantly high or significantly low, anything that's outside the 5% range. And there's nothing more than just this become a number that we're comfortable with in statistics. You know, if we're within 95% of the mean, we consider that to be normal. And no pun intended, there's a normal distribution, but we look at it to be at the right interval. If you're outside of the 95% interval, then we look at that being a significantly high chance or significantly low. Not meaning there's a high chance that's going to happen. It means you're in the rare spot. My issue with blindly always throwing 5% at everything in real life, it doesn't fit everything, right? Just look at the coronavirus right now. You know, the death rate is not 5%. I would not argue with anyone that I would tell them that the death rate is not significant because it's not 5%. So that's why books always push this 5% like it's written in stone when it's not. I think what you have to do as a statistician or someone doing analysis is you gotta kind of distinguish what you think to be high and low, right? If you're making product for a company, then yeah, maybe the 5% is not too bad. As long as all of our product falls within the 95% rule, then hey, we'll ship it to the customers and I think everybody will probably be okay. You know, so, but if I'm making some precision machining, 5% might not be enough. If I am going to implement a new drug to the FDA to try to combat some kind of virus, and I tell them, hey, 5% are going to die from this, the FDA is probably not going to like that number, right? So that's where I don't like the 5% rule so much. But what you got to think of is when we look at things as significant high or significant low, you, as the person doing the analysis, has to decide, you know, is that okay, right? And that's kind of what this kind of gets to, is being outside of there. And sometimes it is, like if you look at, you know, where do we classify the top 5% of the class that graduates college, right? And we can find that value out. You know, we can take out that upper tail of the 5% of the significantly high GPAs. That's why it's called significantly high, because it's outside of the range of what we would be comfortable with. Oh, the reason I just like to spend on it, because a lot of people that read the stats books, I feel like the stats books just really focus on this so much, and for students learning it, it feels like I really should pay attention to this because it's extremely important. And I think what you really should pay attention to is you doing the analysis has to decide if that's a acceptable rate or not. So this goes back to what you were asking, I think, about a week or so, Kyle. When you see on the things on the news, when they do surveys and they say within 5% or plus or minus 5, that's what they're kind of talking about. They're giving them, they've cut their interval now, or we're saying, hey, we're confident that we're inside this range. And that's where those figures come from. And then when you take statistics, I'll actually show you how to calculate that precise point. And that's confidence intervals. When we get into confidence intervals in chapter 7 in stats, you'll be able to actually calculate the precise point of where that interval should be at.
Sweet.
Have you ever heard of the sigma 6 rule?
I have not. I've heard of the range rule of standard deviation, which may be similar. What is the sigma 6?
Well, sigma 6, it's just it's you're using a percentage error. It's in business and like manufacturing for quality assurance. A lot of times they go out to 1 in 100,000 instead of 5%.
Okay, perfect. Yeah,
just tells you that, like, yeah, the 5% isn't written in stone. There's other, I don't know what schools of thought where you use different percentage.
perfect. Yeah, that's good to know. And I don't know. We don't talk about these in the books, right? Because everywhere I've always gone, usually when I do statistical analysis, the company will tell me what their threshold is. And then I just use their threshold, you know. But ever since I've been teaching, every stats book we've used for all our teaching, it just throws us 5%. Like, and the Pearson book for 135 is horrible. Almost every question, it finishes with that question: is this bad because it's in the 5%? And it just really beats it in, and I just don't like it. No, I didn't know that one. That's good, because if you're making product, right, you know, you're not sending out every item you send out is not perfect, unless you are doing maybe precision machining, right? But that's why we have QA, right? Because you have people that walk the floor when you're building things that are checking to make sure everything is being produced correctly. And they do this in everything. Casinos have this. Casinos have statisticians on the staff to make sure the machines are paying out within the right range. So at the end of every night, they pull all the data from the little slot machines. A statistician reviews it and sees if a machine is not paying within the right proper range. And again, they before they go to do analysis, they are given the high and low limit to make sure they're inside some percentage range. And that's kind of what we use this for. And where this 2 comes from is basically saying, hey, I want to be within plus or minus 2 deviations, right? Which is where I get, like I said, the 95% from. So I think I've beat that up more than enough. And I've already talked about we can use technology to do all this stuff versus tables, but we can play with that here in a minute. Any questions on the normal distribution? Now, Dylan brought up a good point about him asking, do we only teach the normal? This is my issue with a lot of degrees, and I understand why, because they're not trying to make you statisticians, but a lot of people take intro to statistics, which is what 135 is. And all we learn is the normal distribution. So people leave and like, oh, this isn't too bad. And then they try to apply the normal distribution to every problem in the world. And it's perfect if the problem in the world is normally distributed. If it is not, then doing these calculations and using a z-table is not going to answer your question, because your data is not normally distributed. So these values won't be accurate. And it happens a lot, especially in the medical field. There's been a lot of papers published where come to find out that their statistical analysis was wrong. They didn't make any calculation errors. Like, their arithmetic was correct. The problem is they thought something was normally distributed, so they used the normal tables, but it wasn't normally distributed, so all their values were misleading. So that's where I like to spend my time in statistics, is making sure your data is bell-shaped before you just start using these tables. So we go on to linear regression, and I realized I didn't put a lot in here. So I'm going to talk a little bit about this, but I think I'm going to more jump over to our scatter plot in Excel. I think that'll be easier to see. And we'll kind of just talk some basic concepts, and we'll probably just call it a day. So if I bring back up our chapter 8 answers again. and I'll add some more to that regression piece. I go to my scatter plot, and I go back to new share to make sure they were all in the same Excel. And this is the one I've already loaded, right? And we've already, and this is a good topic for us to discuss not quickly, but I think today would be more than enough. Because this lesson and our linear model lesson that we already have are basically the same. Different names, same exact concept, right? So in our math modeling class, right, we learned that our formula was y equals mx plus b, right? That was chapter 5.1, I think. If I remember off the top of my head correct. Where m was the slope, and b was our y-intercept. And y and x are what we were trying to compare here, right? And so this is one we've already talked a little bit about when we got into 8.2, graphing data. This is a scatter plot of our x is the number of chirps per second for a striped ground cricket. Our y is the temperature it is outside, and we wanted to see if our data fit a linear model. So we easily go back to 5.1 and do like we did with 5.1, right? And what we did with 5.1 is if I click on this just and add Trendline, and we do linear, this is where we tried all the different types before, right? And where I get the display equation? That's what I guess the options. Display R squared, display equation on the chart. Okay. I'll move this guy over here so we can actually see him. We get our equation. So y equals 3.3x. So our slope is 3.3 and our y-intercept is 25 degrees, right? And we get this value called an R squared, which is, I can't remember off the top of my head what that actually stands for. I'd have to find my regression book. But what our book goes into more is it wants R. So bring up my little pencil. It doesn't want us to use R squared. It wants us to use R. When R is what was in my thing, a correlation of coefficient. So if I jump back here just for a minute, and I go back to my share. I get rid of my pencil for a minute, share. This correlation of coefficient here that we have to do all these tables on is our R symbol, all right? And I'm gonna add some more notes to this so you guys can go back and kind of look. I don't think I'm gonna test you on linear regression just because it's a very much tech savvy, and I don't wanna spend much time trying to figure out how to do this technology-wise. So I go back to our Excel just so we can understand how this all works. Yeah, that's what I want. So to go from R squared.
According to Google, R squared is the, never mind. Can you hear me?
Yeah.
Hello? Am I a robot?
Nope.
Okay, so I Googled R squared. It's the goodness of fit for your regression line. So
Oh, really? I have not heard it called that before.
Goodness of fit?
I've heard of goodness of fit, but I've never heard of R squared. I thought it had a different name. Now I want my regression book. Not saying I'm saying Google's wrong, because Google knows everything, so I'm not doubting Google.
I don't know. That's what, when I looked up regression lines,
Yeah.
R squared, and it is between a 0 to 100% scale. So I guess it's like if you got an R squared of 0.697, what is it, like a goodness of fit of like 70%?
Yeah, pretty much.
So then if you had your scatter plots way away from that line, you'd have a lower R squared, I'm imagining.
Right. Here we go, least squares line. That's what it's called. This whole thing is called.
Oh, yeah. Well, the line is the least squared line, right?
Yeah. There we go, R squared. I just see that.
This is all coming back to me.
Does anyone give it a name? Just calls it the variation in this book. The variation in the residuals. And that's what I always call as R squared, but I know it does have. And this is my issue with statistics, honestly. And I love statistics. Is there's no hard name for anything. And so everyone calls it a little bit different, but the concept is the same. So you can see, I got a R squared of 0.697. The correlation of coefficient is R. So if I go to XL, how do I get from R squared to R? I take the square root. So square root of 0.69747. And I get a correlation of coefficient of 0.83. And both of these are percentages. So my correlation of coefficient has to be between 0 and 1. My R squared has to be between 0 and 1. The reason it depends on the book and who you talk to about their analysis. You want your values, either one, R squared or R, to be close to 1. Right? So if you look at your R squared, you might be like, that's not really that close to 1, so I don't really like this. But then when I find my correlation of coefficient, that is much closer to 1, right? Both of these values, though, tell you basically, is this a good linear model or not? That is the big takeaway, no matter which value you use. Is this a good model? And the reason my R squared is so low, if you look at it, I have this cluster, right? And there's statistics classes that are dedicated to nothing but this, just regression for a whole time. Not at our college, but at 4 years in grad school, because that's how widely this is used. But the reason I have this R squared value like this is this cluster right here. Because basically what R squared is doing, and now I'm getting more into the math instead of the theory, is it's finding the distance between the point and the line for every single data point. And it is taking the ratio between the sum squared error and the sum squared total. Now we're getting way into more into calculations, that stuff that we don't have to worry about for now. We can easily talk about these later if we want to talk about them more. But that's what it's showing, and that's why this value is still low, is because of this little blurb right here. And honestly, why I think this value is so low is our sample size is way too small, our N. Because you got to think, we have what, 1, 2, 3, 15 here? Only 15 data points to compare. All right, if I really want to do regressional analysis, I should probably add a couple of zeros to this thing and get about 15,000 crickets. And then I could probably get a good model. But even with this small 15, right, I'm already starting to get a decent linear model. So what you're supposed to do with this correlation of coefficient is you're going to go and compare your value to a value in the table, right? I have never even done that ever, except for when I teach it because it's in the book. I just look at this number, right? I know a correlation of coefficient is greater than 0, but less than 1. 0.83 is pretty close to 1, where I'm going to say I am good. The only time I've seen things fail on the table is when you have a sample size of less than 10. And I don't know why you'd ever do regressional analysis with something that small. So this table doesn't even get used in the real world because nothing is ever this small.
Can we try deleting 5 points and see what happens?
Sure. Clear all my mess out. Clear this out. So are they in order? Nope, they're not. So I will just leave out the bottom 5. Is that 5? 1, 2, 3, 4, 5. Yeah, I'll leave out my bottom 5. So again, I highlight, charts, scatter. So there is, I just picked the bottom 5. So I don't, now if I add a trend line, so I'm going to do linear It's already highlighted. I want to display my chart and my equation. And there is my new value. And if I want to find its correlation or coefficient, I take the square root, SQRT, there we go, of 0.83001. And now my correlation or coefficient, Command X, Command V.
I think we got lucky there.
No, I mean, it went up because I ended up taking, yeah, it looks like I did. I ended up taking out those bottom three. No, I didn't. No, I took out the top two, and this one that was here, and one of these here. So it looks like I took out some of the higher ones, which dropped my line down, which increased my slope.
Oh.
But what the table does is when you have a smaller n, the value comparing it to is much higher.
Yeah.
So that, and if you Google correlation coefficient table, you'll see the numbers when the tables are smaller are much higher. You have to compare this to, and as your n increases, that number drops down because it gives you more room because you know it's going to automatically drop because I have more points that I'm taking in consideration. Because you see our R squared went up by a lot. It went to from 0.69 to 0.83, but my correlation or coefficient only went up 8 points. And this went up almost 14 points.
Now, theoretically, if you had 2 points, you'd have R squared of 1.
That's right. You'd be a perfect line, right?
Yeah.
So what regression, and I think Kyle brought this up. What you use regression for is to see if things have relationships. And Kyle brought up the example of murders, death rates go up during when ice cream sales go up. There was another weird one too, where it was the price of pig feed in some like third world unknown country has an effect on our stock market. So yeah, that's where you have to be careful with the regressional analysis. And this is where I think it is used so horribly wrong in the real world. Because we always have these things called lurking variables. And we as humans need to be a little smarter than we are sometimes. And because we blindly follow the math, because we've been taught at such a young age that if you do the math correctly, then math is right. Well, yes, that is true. The arithmetic is correct, but math, I've gotten more into mathematics, math is more than calculating, right? You have to interpret the results. And so like Dylan just said, if I take just 2 points, I'll get a perfect R squared and then no one can argue with me. That is a perfect line, right? But I shouldn't take two things and compare them and then make judgment on the rest of the world. And hopefully a lot of you, if you're following anything that's going on with the coronavirus, you can see, depending on what news station you click on or what politics you want to believe, you definitely have some people really misinterpreting the data a lot. I did hear an interview this morning using statistics. The mayor of Las Vegas, yes, where the casinos are, started trying to be.
It's hard to trot there.
Yeah. She's trying. You see, did you hear us try to throw some good statistics terminology around? I'll give the reporter credit. He knew what those words meant, so he kind of put her back in her place pretty quick.
Yes.
But she was talking, if for any statistical analysis, you have to have a observational group, a controlled group, as she called it, which you do if you're doing an experiment, which is what we do in the medical field. I don't know if I would be happy if I lived in Las Vegas if my mayor is now telling me I am going to be part of the control group and the test bed of the country for coronavirus. So that was pretty interesting to hear her say. She quickly tried to backtrack on her words and say, that's not what I'm saying. Don't put words in my mouth. But yeah, that's exactly what you said based on the statistical words you just used. And that's where regression gets people in trouble, because you can see I didn't do any math here, right? I just trusted Excel. I did a scatter plot by hitting insert chart. I right-clicked on a point and I said, add a trend line and give me my line in R squared. And now I can go on my local network and tell everyone in the world that cricket chirps are causing global warming. Because I have proof here. I have a good R squared. I see that as the number of chirps increase, so does the temperature outside. So the crickets rubbing their legs together to make these chirping sounds are what's causing global warming. And I have the math to prove it. So it has to be true.
I knew it.
Yeah. Might be without a job soon. So that's where you have to be careful, right? And that's why I don't spend so much time on the calculations at this level, because most of you aren't going to have to do the calculations. I would love to sit down with anyone that wants to go through how to do all these calculations. But what I would rather is people realize is, hey, we got our variables backwards. The temperature should be down here where my chirps are, and my chirps are probably should be where my y is, because x typically leads to y.
Yeah.
So as the temperature increases, right? So if I regraph this, copy this guy, Command C, and we'll paste him here. No, I want him to be my new y, so Command V. And then I copy this guy, Command C. Right, and so I've swapped them. And now if I highlight these and insert a scatter plot, the graph looks very similar still. I add my trend line. So I want my chart and my thing. And notice my values, even though it's the exact same data, bring this up a little bit up here so we can see both. My R squared value didn't change at all. However, my line changed a lot, right? Because remember, the R squared is just the difference between the points. So it's the exact same point. So obviously the R squared is not going to change because the points are the same. So all of this other figures are still the exact same as what we've been showing, but my line has changed a lot. So now as every 0.2 degrees in Fahrenheit increases, this is how much more a cricket is going to chirp, right? So that makes more sense. Now, the warmer it is outside, the more crickets are chirping, which is not leading to global warming. It's saying the crickets are more active when it's warmer, very much similar to Kyle's people being killed due to ice cream sales, right? And so where we have to be careful with this, because sometimes it always doesn't make sense. So I'm going to write this out so we can see it a little bit bigger, right? So we have y equals 0.21 x minus 0.31. So remember, our first value is our slope. And then our second value is our y-intercept. Now, the y-intercept is found just by calculating, and that says where this line crosses the y-axis, right? So to get that to happen, x has to be 0. So if I put a 0 in, I get a negative 0.3 degrees Fahrenheit. No, sorry, my temperature is F. So I put in a 0 degrees Fahrenheit, so it's freezing outside. I get a negative 0.31. Well, can crickets negatively chirp? No. So in this case, my y-intercept doesn't really mean anything. It's just a calculation thing, because I can't have a negative chirp, but it basically says, hey, if it's 0 degrees outside, probably not a lot of crickets around right now. So it's okay. And then as my temperature increases, I will get to a point, and I only have to go above 2 degrees that I start getting positive chirps. And again, probably at 2 degrees Fahrenheit outside, not a lot going on for a cricket chirping either, right? So these are where you have to more understand of what the information's telling you, and less on how you get the values. Because I can get Excel to give me the values, but I want to know, what do these values mean? And how do I use them to make predictions of like when I should have things end or not? That's really what I would be more worried about in my regression for our lesson. So I will still go in and put some little more information into the OneNote for you to have, but I would definitely be more concerned with the math modeling and realizing that our correlation of coefficient, the big takeaway for today, is just supposed to be between 0 and 1. The closer to 1 it is, the better that my model is. And like Dylan said, R squared is like what we call goodness of fit, which is the whole chapter of statistics that we don't even get to in 135, at least not in my class. I don't go fast enough to get through it. But it tells you how good your model is. And so the higher your R squared, the better the model looks, right? And just because you have an R squared doesn't mean you have a good model. Dylan hit it perfectly. If I plot 2 points, I have an R squared of 1. That's perfect now, according to the math. Well, it's probably not still a good model. So just because you don't have a high R squared, it's argumentative if your model's still good or not, right? All the R squared is saying, hey, you have a good mathematical fit, which means a lot of your points are following your model, but it doesn't really mean that your model is a good model for what you're trying to use it to do analysis on. Any questions on anything we've covered today?